Bismillahirrahmanirrahim. Assalamu alaikum. Today, inshallah, we'll continue the third class in DC machine. So today we'll describe the steady state analysis for separately excited for shunt and series DC motors, and we'll describe the speed control for separately excited and shunt machines. Last week we described the dynamics of DC motors for separately excited one, and we discussed the construction of DC motors. We drive the derivation or equation of the induced voltage of DC motor. We derive the equation of the developed torque of DC motor, and we describe the different types of DC motor configurations regarding winding, like separately excited, like shunt, long shunt, and short shunt DC motors. Today, inshallah, we'll continue discussing the power flow in DC machines, discuss the shunt and separately excited performance, and also discuss the performance of series DC motor. Then we'll discuss the speed regulation, the speed control of DC motors, and the power electronic converters used for controlling DC motors. Firstly, shabab, for the power flow depends on the connection of the motor, but all of connections are common in some cases. For example, the input power, which is the electrical input power, is the same for all of kinds of motors. So all of kinds, we will have input electrical power, B electrical, okay, which is equal to V terminal multiplied by I terminal. And then we will have some electrical losses, which are the sum of I square R's for all resistance included in the circuit, whatever the connection, series, shunt, or separately excited. And we will have some rotational losses, and the remainder power will be the output power, which is a mechanical power. So after removing the electrical losses, we will have the electromechanical power or converted power, which is EA, induced EMF, multiplied by the armature current. So this power, EAIA, we call it as developed power. It can be calculated either using electrical quantities, EAIA, or mechanical quantities of torque developed multiplied by speed. And for any kind of copper losses in the circuit, any resistance has current, so the copper loss on this resistance will equal to I square R. So, for example, for series resistance, which is connected in series with the terminal of the motor, the power loss will be I terminal square multiplied by R series. For the field winding, it will be IF square multiplied by RF, and for the armature copper loss will be armature current square multiplied by the resistance of the armature. So let's start with the separately excited and shunt motors. Firstly, on the left-hand side, this is the equivalent circuit of the separately excited DC motor. As you can see, we have field winding, which is separate, and we have armature winding. Separate means we supply all of circuits from different supplies. So we have supply for field winding and another supply for the armature winding. So if we make Kirchhoff voltage law for the armature circuit here, we will find V terminal equal to IA RA plus EMF on the motor, and also we may include or consider the brush voltage, which is very small value compared to terminal voltage. And the EMF, as we derived last lecture, EMF equal to Ka, which is the machine constant, multiplied by flux and speed. So if we would like to change the field current here, we simply will change the value of VF, and IF will be changed. This is in order to control flux. However, for the shunt DC motor, as you can see, the field winding is connected in parallel with the armature winding. So we have only one terminal voltage. For this connection, in order to control the field current, we have to add another series resistance. We call it as field control resistance in order to control the field current. So the relation here will be V terminal equal to IARA plus EA, the same like the shunt motor, sorry, the separately excited one. However, for the current, applying Kirchhoff current law at this node, we will find I terminal equal to IA plus IF. So here, in order to calculate EMF has the same relation, motor constant multiplied by flux multiplied by omega m. However, here phi is controlled or changed with the circuit because we have armature, we have controlled field resistor here, so we can represent the relation in terms of IF. So the relation for EMF will be motor constant multiplied by IF multiplied by the motor speed. This is for the shunt one. For the characteristic, شباب, if we would like to plot the characteristic of torque speed, simply we have the relation EA equal K phi omega, which is equal to V terminal IARA. We would like to get omega in the left-hand side, so reformulate the equation. We'll find omega equal to V terminal minus IARA divided by K phi, and we can substitute IA by the value of torque divided by K phi, so the relation will be like that. V terminal divided by K phi minus RA divided by K phi squared multiplied by torque. So simply by applying small program and change the value of T and find the value of corresponding omega m, we will find the relation of the torque speed like that. In the horizontal axis representing torque or current, and the vertical axis represents speed, you will find the characteristic of separately excited or shunt in this linear curve. Right. And later we will discuss how we can control this curve in order to control speed based on these parameters. For the series motor, because the series field winding is connected in series with the armature winding, so we have armature resistance, we have rheostat controlled resistance, and we have series field winding as seen in this figure. So the field current, which is moving in the field winding here, is the same like armature current. So we expect to have the relation of Ka multiplied by phi, machine constant multiplied by flux, will equal to another constant which is called K series multiplied by IA, because IF equal IA in this circuit. So we can write the relations in terms of K series. For that, the EMF will equal to K series IA omega, and torque will equal to K series multiplied by armature current square. Simply, we can get the value of omega, or the expression of omega, by the same way, and we can find that the characteristic is moving like that, شباب. This means at low torque or high speed, we have low torque, and at low speeds, we have high torque. Actually, this is very important for the application which needs high starting torque. So we prefer DC series motor for such kind of high starting torque applications. Type. There is an important term called the speed regulation. This term is used for any kind of motors. However, we need it here in particular for DC motors. The speed regulations, from the definition, we'll give an example in order to understand the meaning of speed regulation. And if we have a load applied to DC motor and the load torque is changing, so we expect the speed will be changed as well. If the difference between the full load speed and no load speed is small, so the term voltage regulation, which is omega no load minus omega full load divided by omega full load, will be small value. And this will be very important. So if the speed regulation for any DC machine is small, this will be perfect machine. However, if this ratio is high, this means this motor is not preferred. So we need to calculate speed regulation for all of kind of motors in order to know if this motor is good or not. Like how we can calculate the no-load speed? No-load speed means speed at zero torque. So on the characteristic here يا شباب, at torque equal 0 or virtually IA equals 0, we will find the speed of the machine, which is called no-load speed. So in order to calculate this speed, we know the relation of omega equal to EMF divided by Ka phi. If we substitute with the relation of EA for separately excited DC motor, for example, it's V terminal minus I no load multiplied by RA divided by Ka phi. So here, شباب, we can consider no load current multiplied by RA as very small voltage drop. So we can consider the relation of omega no load equal to V terminal divided by Ka phi. We have an example here. First, 25 kilowatt 250 volt shunt motor has an armature resistance 0.25 ohm and field resistance of 125 ohm. There is very important notes here, شباب. You can see the field resistance is very high compared to armature resistance. This is normal because the field current is small compared to the armature current. The role of the field current here is to create flux for the machine. However, the armature current represents the power of the machine. So for very high power machines, you will find very high armature current and very low field current. For that, we need high resistance for the field current. Sorry, for the field circuit. So at no load condition, the motor current is 12 amps and the speed is 1000 RPM. What's required here? First, draw the equivalent circuit for this case. We know the case here is shunt motor. So simply we can plot the armature circuit in parallel with the field circuit, and we can write the values of resistance 0.25 for armature and 125 for field resistance. Second, calculate the motor constant. For shunt motor constant, شباب, you know the relation of EMF equal to K multiplied by phi multiplied by omega. We can represent the motor constant here as K multiplied by IF by omega. So the required value here is K. What is the motor constant K? So simply we have one case, which is the no load case. We have the 12 ampere armature current, sorry, motor current, which means the input current to the motor. And we have speed of 1000 RPM. So simply we can calculate first the current, which is moving here in the field circuit, which can be calculated by terminal voltage divided by the field resistance. So IF equal to 250 divided by 125 ohms, which is 2 ampere. So the armature current at no load, شباب, will equal to the total current or terminal current minus the field current, which is moving here. So the armature current will be 12 minus 2, which is 10 amps. In order to get the machine constant, we need to calculate E, and we need to calculate omega in order to calculate the machine constant. So we can calculate E here simply by V terminal or VA minus IARA. So just substitute and get the value of induced voltage. As you can see, because the no load current is small compared to full load one, you will find the EMF is very close to the terminal voltage. So here 247 and the terminal voltage is 250 volts. Right. Also, we can calculate the no load speed. So no load speed, we have here the no load speed as 1000 RPM. So we can get the corresponding value in rad per second, which is 104.7 rad per second. And then we can substitute in the relation E equal K multiplied by IF and omega and get the value of Ka. يعني take care here because the field current is inserted in the circuit for shunt motors. We have to consider the machine constant independent to the other terms, which is IF and omega here. But for separately excited DC motor, because field current is not exist in the model, we calculate Ka multiplied by phi as a constant. So here we can calculate Ka, which is EF divided by IF multiplied by omega, and get the value of Ka. طيب. طبعا this is voltage divided by rad per second, the units of Ka. Next, it's required to calculate the speed and torque at full load. Simply, شباب, at full load, in order to know the full load values, return to the problem again. In the beginning here, it's written 25 kilowatt, 250 volts. So this means the rated power of the machine is 25 kilowatts, and the terminal voltage is 250. So in order to get the rated current, we can divide the rated power by the voltage and get the rated current. So this is the full load current of the machine, full load input current. To get the armature current, so we have to subtract the field current value, which is 2 amps, which is constant here, will not be changed because we don't have control for field control resistance. So the armature current here will be 98 amps. We can substitute to get the generated or EMF voltage for this case at full load. So VA or V terminal minus IARA will equal to 250 minus armature current multiplied by armature resistance, and this will be the value of EA at full load. If we compare this value, شباب, with the value at no load, we'll find no load EMF is higher than full load EMF. This is normal because the current here is high. So we need to calculate the speed and torque. Simply, we can say now omega equal to E divided by Ka phi or IF, because this is shunt motor. So we have E and we know the value of Ka and IF, so we can simply calculate the motor speed. This is in rad per second, and we can get the corresponding value in RPM. As you can see, شباب, here the speed is lower than the no load speed, which was 1000. This is normal because when the machine is loaded, the speed will be reduced. We need to calculate the speed regulation, so simply substitute in the equation speed at no load minus speed at full load divided by speed at full load, and we can get the value of the speed regulation. Yani for the speed regulation value, if it is less than 20%, we can say this motor is good. So 10% is accepted. In order to calculate the torque at full load, we have now the value of IA and EA. So simply we can get torque from the power or developed power equation. We know developed power equal torque omega or equal to EA multiplied by IA. So simply we can substitute in the relation here and get the value of torque. So the torque here is 230 Newton meters approximately. Another example, شباب. A DC motor develops a torque of 30 Newton meter. What is required here? To find the torque when the armature current is increased by 50% and the flux is decreased or reduced by 10%. Yani this is in order to recognize the relation between torque and armature and field currents. So simply, شباب, we have the relation of torque equal to K, machine constant, multiplied by phi IA. So we can get the relation between torque and phi and I. طبعا phi, شباب, is a function of the field current, and Ka depends on the machine constant, which is almost constant for all of kinds of operations. So we can say, if we compare two cases together, T1 divided T2 will equal to phi1 or IF1 multiplied by IA1 divided by phi2 or IF2 multiplied by IA2. So this is for the two cases. So comparing the two cases together and get the values of phi2 and I2. It's said here in the problem, the armature current will increase by 50% and the flux will be reduced by 10%. So we expect IA2 to be 1.5 of IA1 and phi2 to be 0.9 of phi1. So simply substitute in the relation to get the value of the second torque. So as you can see here, torque is higher than the first torque by just increasing the armature current, which means the power will be increased. So this is an indication for the higher torque. And also reduction in the flux. Reduction in the flux means the speed will be increased as well. So the torque will be increased and the power also will be increased because of the speed increase. Another example here, Shabab, for DC shunt motor. 250 volt DC shunt motor has an armature resistance of 0.1 ohm and field resistance of 250 ohms. At full load, its input power is 14 kilowatts. So this is the condition of rated or full load at 250 volt. And its rotary speed is 1000 RPM. Calculate the speed regulation. طبعا simple شباب, for speed regulation, we need no load speed, full load speed in order to calculate the speed regulation. So firstly, from the rated power, we can get the line current of the machine or input current. So simply by dividing the rated power, which is 14 kilowatts, divided by the terminal voltage, which is 250 volt here, to give the input current of the machine at full load. Right. For the field current equal to V terminal divided by RF. So we can calculate the field current and get the rated armature current here, which will be 55 ampere. In order to get the speed, we need to calculate the speed at full load. We need to calculate the EMF and K phi. So simply at full load, we have now the current value of IA, so we can calculate EA simply. For K phi, Shabab, we can calculate K phi using EA divided by omega or N. Take care, if we divide it by omega, the units will be voltage divided by rad per second. But if we divide it by N, the units of K phi will be volt divided by RPM. And you can calculate in both of ways, but you have to unify your units in solutions. So we can calculate at 1000 RPM, which is the full load speed here, okay, to get the value of K phi. And now we can calculate the no load speed based on what? Based on the assumption of the no load current will approximately equal to 0, or the voltage drop across the resistance due to no load will be equal to 0. So we can assume that no load speed equal to V terminal divided by Ka phi. And we can get the value of N in RPM. طبعا شباب, if we have the value of no load current, we can substitute in the relations and get the actual speed. However, because we don't have here the no load current value, we can assume 0 no load current and get the speed at no load in this way. Simply, we can substitute in the equation and get the value of speed regulation. Okay. Another example related to the steady state analysis of DC machines. 220 volt 7 horsepower series motor is mechanically coupled to a fan and draws 25 amps and runs at 300 RPM when connected to 220 volt supply with no external resistance connected to the armature circuit. The torque required by the fan is proportional to the square of the speed. This is extra words in the problem, because we know, because the fan load all of time, the torque will be proportional to the speed squared. So it can be omitted from the problem, and you have to recognize that for fan load, torque load will be proportional to square of speed all of time. Considering the armature resistance 0.6 ohm and the series field winding resistance is 0.4 ohm, and neglect armature reaction and rotational losses, okay, so determine the power delivered to the fan and the torque developed by the machine. So this is number one. It's required to get the developed power and torque at case of the full load, which is given in the problem. So simply, we have the armature current, which is 25 amps, and we have the speed also, which is 300 RPM. So simply, we can calculate E terminal, or EF or EA, which is equal to V terminal minus I multiplied by all resistances of the series motor. For series motor, we have armature resistance, we have series field winding, and rheostat. All of these resistance are connected in series. So here we have 0 rheostat, so we can substitute armature resistance 0.6, armature series resistance 0.4, and rheostat is 0. Taban, we have to recognize very important thing here. As you can see, the series resistance is 0.4 ohms. It's very close to 0.6. We said before, series resistance is the equivalent resistance of the series field winding. We described in shunt and separately excited, the field winding is very high. However, if it is connected in series with the armature winding, it has to be very low in order to work with the high current of the armature. So as you can see, the field winding here has very small resistance because this is a series motor. So simply, we can calculate the EMF of the machine, which is 195 volt here. We need to calculate the developed power, so simply we can multiply EA by IA to get the value of power. So this is the value of power in watt, and we can divide by 746 to get it in horsepower. In order to calculate the developed torque, we need to divide this power by omega, and we know the value of omega at full load, which is 300 here. So simply we can substitute in the relation to get the value of the applied developed torque. Number B, the speed is to be reduced to 200 RPM by inserting a resistance RAE in the armature circuit. So we will use here rheostat in the circuit. So if we add a resistance, we expect to have different operating points. What is required here? Determine the value of this resistance and the power delivered to the fan. So we add the resistance in order to decrease the speed to 200 RPM. So this is a method for speed control of series motor. When we add resistance, we can decrease the speed as has been happened here. Right. What is required here? What is the value of added resistance to keep the speed at 200 RPM? So simply, you know the relation of torque. We said it's fan load torque here, so we know torque equal to K series multiplied by IA, or armature current, square. We can calculate K series from the first case in order to use it in the second case. So simply, we have the first case torque and we have the first case current, and we can get the value of K series. Now for the second case, we need to calculate the resistance. And in order to calculate resistance, we need electrical quantities like current, like EMF, but we have only here the relation of torque. So we need to use the torque here with the RPM in order to get the new electric torque for the motor at the 200 RPM. Simply, we know for this load, it's fan load torque, so torque is proportional to omega square. So we can say T for case number 2 divided by T for case number 1 equal to speed for case number 2 divided by speed for case number 1. So simply, we can use this relation to get torque at 200 RPM, which is case number 2, equal to 200 square divided by 300 square multiplied by the first value of torque, So we get the new developed torque of the machine. This new torque equal to K series multiplied by armature current squared. So we can calculate the armature current in this case. And simply we can calculate now EA, which is the armature, the EMF voltage here, which is equal to K series multiplied by IA multiplied by omega M. And we have all of these value for second case, and simply we can calculate the EMF. So now we have the EMF and armature current, we can simply apply Kirchhoff voltage law and get the missed value of resistance, which is RAE. So finally RAE here is 7 ohms. طبعا شباب 7 ohms, this means you will have high losses because the current here is 16 amps. So 16 amps squared times 7, you will have a lot of losses here on the resistance or the rheostat itself. So it's required here also to calculate the developed power. So developed power will be EAIA, which is equal to E, this value, and multiplied by IA. This will give you the value of the developed power. Okay. Right, we have 2 questions here. Muhammad is asking, RAE stands for, it's rheostat resistance, rheostat external resistance. Is there any question up till now, Shabab? Regarding speed control, Shabab. For the separately excited and DC motor, now we know the characteristic. This is the characteristic of the DC motor. As you can see, this is no load speed, and this is the curve of speed versus torque. If we would like to control this characteristic in order to control the load speed, and for instance, if we have load torque like that, torque load like that, Shabab, for fan load, for example, and we need to calculate the, we need to make speed control for this load. So simply, if we move this characteristic down or up, will it change the value of the speed? So this is the idea of speed control now. In order to move this curve up or down, we can control the parameters of the equations here. As you can see, omega m is proportional to V terminal minus IA RA divided by K phi. So simply we can control the value of RA by adding resistance. We can control the terminal voltage by changing the value of voltage applied to the motor. And we can control the field by controlling the field current. So we have 3 different techniques to control the DC motor speed: by adding resistance to armature winding, by terminal voltage control, and by field current control using rheostat. First way is by adding resistance. We can see here, Shabab, this is our relation, and here is the added rheostat resistance for the armature winding. By controlling this value of resistor, we can find that. If we know the relation for speed at no load, you remember we said speed at no load equal to V divided by K phi omega. Sorry, K phi divided by K phi. Speed at no load equal to V divided by K phi. So it's independent on the resistance value. So by changing the resistance, for all of time, the no load speed will be the same. However, when the current is high and torque is high as well, you will have different values of speed. So by adding resistance in this way, we will have different characteristics like that. So you can control now the speed. So we can assume that we have different speed at this point, that point, and so on. So by adding resistance, we can control the motor speed. This is the first type. Second type is the terminal voltage speed control. As we described in the equation, if we change terminal voltage, the speed will be changed. However, for terminal voltage control, the no load speed also will be changed because no load speed equal to V divided by K phi. So as you can see, all of the characteristic is moving down if we decrease the voltage. And if we increase the voltage, the characteristic of the machine will be moved up. However, we have limitation for increasing voltage. As you know, for any kind of machines, you cannot increase the voltage over 10% of the rated voltage. Otherwise, you will affect the insulations of the winding. So we have limitation for increased voltage here. So this is the way of increasing or decreasing voltage for the machine. And the limitation is up to the base speed. So it's better to not increase the voltage after the base speed of the machine. This is for the voltage control with separately excited DC motor. Right. What is the advantage of this method, Shabab? As you can see, it provides smooth variation of speed control from 0 to base speed, because we can start from any point to base speed at each characteristic. So you can start from very low speeds to high speed. Secondly, easily controlled by solid state drives. It's very easy to control the armature resistance using solid state drives, and we will describe, inshallah, how we can control this. The last one is its constant current and torque are easily achieved. It's very easy to control the current to be constant with this type. We will describe, inshallah, the block diagram for constant current control of this method. So these are the three advantages of the voltage control. I believe we forgot to mention the adding resistance drawbacks. It's written here, the disadvantage of this method, because we add resistance, so it's expected to have higher armature losses. The third technique, which is field current speed control. As you can see, Shabab, when we change the field current, we will have similar characteristic like in voltage control, because the no load speed is proportional to the inverse of field current. So if we increase the field current, the no load speed will increase, and if we decrease the field current, the no load speed will increase. So this is simply the characteristic, and this is the direction of increasing field current. Right. How can we increase the field current? Simply by insert a series, or let's call it field control resistance, and we can start at 0 control resistance, like in this case, and this will be the value of IF, and this is the corresponding speed. And if we start increasing the value or RF control in this direction, you see, because the field resistance and the added resistance will increase the value of the branch, so the current will be decreased, and this will increase the speed of the machine. And we have limitation for that, which is the maximum speed of the machine. So this is the third technique for speed control. But we have limitation also for decreasing current, because we may decrease the current and the speed will be very high. So, and if we have zero field current, theoretically the speed will be infinity. So, we have some limitations now for field resistance control and for voltage control as well. So, we can combine both of them in one control system, and we have to consider that with a speed lower than base speed or no load speed, we can use voltage control. And we cannot increase the voltage control again beyond the base speed. However, higher than base speed, we can start using field control. طبعا, if we use voltage control in the first part, we have to make constant torque operation by constant current operation. So at this part, we can increase the power of the machine because the speed is increasing from 0 to base speed, and the torque is constant, so the power will be increased in that way. However, beyond the base speed, it's better to reduce the torque in order to not making the machine overloaded. So we make it as constant power control. So to keep constant power control, it means we can increase the speed. However, the torque has to be decreased. So this can be achieved by field current control. So this is the technique which is preferred for DC machine control. Here is an example. 240 volt DC shunt motor has an armature resistance of 0.25 ohm and the field resistance of 120 ohm. At full load, the armature draws a current of 40 amps and speed is 1100 RPM. المطلوب, find the developed torque, then find the field rheostat. If the field rheostat is adjusted so that the field resistance is 150, find the new operating speed if the torque and the armature current remains constant. So we have two parts here. The first part is regarding full load operation of 40 amps, and we need to calculate the developed torque. So first, the generated EMF we need to calculate in order to get the torque. So EA equal to V terminal minus IARA, which is V terminal 240 minus 40 ampere multiplied by the armature resistance. So we can get the value of generated or EMF voltage. Simply, we can calculate the speed. We have the speed already of 100 or 1100 RPM, so we can get the corresponding rad per second speed, and developed torque, we can get it by dividing developed power over speed. So B developed equal to EA multiplied by IA, and developed torque equal to this developed power divided by omega. So we can get the developed torque. Second, again, let's read the question. The field rheostat is adjusted so that the field resistance is 150 ohms. So we are going now to change the field rheostat of the shunt arm. So we expect to have lower field current. Find the new operating speed if the torque and the armature current remains constant. So we will make a control on the armature current to be constant, and the torque also will be constant. So what will be the value of speed for the next case by adding the resistance? The initial field resistance was 120 ohm at the new field rheostat, and RF2 equal to 50 ohms. So the initial field current can be IF equal to V terminal divided by RF. So it's equal to 240 divided by 120. So this is the IF in case number 1. For case number 2, IF equal to V terminal divided by the RF2, which is 150. So the IF2 is 1.6 amps. So comparing first case and in the second case, you will find the field current decreased. So the armature current remains the same This means that the generated EMF is the same for two operating conditions, because we have a constant current and constant torque as well. So if E is the same for both of cases, we can say that Ka, which is a machine constant, multiplied by IF1 omega 1 equal to K2, or Ka multiplied by IF2 omega 2. طبعا K is based on the machine design, so it's constant. So we can compare now the two field currents with the two speeds to get the value of the new speed. So this is example to see what will happen if we control the torque to be constant and decreases the field current. So as you can see, the machine speed increases. Right. Another example here for the constant voltage, for voltage control and field control together. Okay. By the way, this curve is called in some books as Ward-Leonard method. Ward-Leonard method. I will write it down, inshallah, for you. So here, the example is said, variable speed drive system uses separately excited DC motor that is supplied from variable voltage source. The torque and power profiles are shown in figure below. This is the figure. The drive speed is varied from 0 to 15,000 RPM, which is the base speed here, by varying the terminal voltage from 0 to 500, with the field current maintained constant. So we speak now about this part. What's required here? To mine the motor armature current if the total the torque is held constant at 300 Newton meter up to the base speed. So let's start with the first part. So we have base speed is 1500 RPM, terminal voltage is 500, so very close to EA at no load speed. So we can calculate K5 from this condition. So it's equal to V terminal divided by the no load speed, and this will be the value of K5. As you can see here, we calculated K5 totally as one constant, because this is separately excited DC motor and the field current is not going to be changed. So we can simply calculate the armature current now, shabab, by dividing torque by the Ka5 and get the value of armature current for the first case. And the previous here. Yes, this is required for the first case. Second case, the speed beyond the base speed is obtained by field weakening. Field weakening, shabab, means decreasing the field current. Field weakening means decreasing the field current, and in this case, the machine speed will be higher than the rated speed or the no load speed. And this field weakening is valid for all of kind of machines, not only for DC machines. So for all of kind of machines, we can make field weakening to increase the machine speed, and the applications for this field weakening is in applications of electric vehicles and aircrafts. Type. What is required here, shabab? The speed beyond the base speed is obtained by field weakening, while the armature voltage is held constant. So for now, the voltage will be constant at 500. What's required here? Determine the torque available at speed of 3000 RPM. As you can see, the no load speed was 1500. Here we need to reach with the speed to 3000 RPM. If the armature current is held constant at the value obtained in part A. So using the same value of current in part A, and it's required to calculate the torque at 3000 RPM. So the speed now is 3000 and the terminal voltage is 500, and it's approximately equal to EA because the and it's very high speed and the armature current will be very low. So we can calculate K5 by the same way, which is V divided by N or omega because we multiplied here by 2 by 60. So this is the k phi in volts per rad per second. And simply we can calculate the torque, which is equal to k phi multiplied by the same current, because it said the current will be constant. So this will be the torque in the second case.